Hi guys, in this video we're going to look at addition reactions, another type of organic reactions. And addition reactions occur when you have an unsaturated species, a species with double or triple bonds. And an example would be an alkene. An alkene is a species with a carbon-carbon double bond. And this double bond is a region of high electron density. And this region of high electron density here will attack electrophiles, things with a delta positive or a positive. Now, consider we've got this molecule, which I'm just saying is YZ, and we've got a delta plus there and a delta minus there. Then this region of high electron density will attack or be attracted to the delta Y, the delta plus portion of the molecule. And it's going to use the pair of electrons in that bond and form a new carbon Y bond, and that can be shown by the following curly arrow. What the curly arrow is showing is that the pair of electrons in the carbon-carbon bond is now being used to form a new YZ bond. As this bond starts to form, then this YZ bond needs to break. And remember, when bonds break heterolytically, pair of electrons always go to the most electronegative atom, the one with the delta minus. Now, as a result of the pair of electrons moving from the carbon-carbon double bond to Y and the pair of electrons from the YZ moving to Z, we get the following species. Remember, our curly arrows need to tell a story of where the electrons are going to in a reaction. And what we get then is the following. We get the following intermediate species, but there is something missing from this structure. I wonder if you can think about what it is. This carbon here has an equal share of 4 pairs of electrons. But here, the carbon now is only an equal share of 3 pairs of electrons. So in effect, it's an electron down compared here. It's an electron down compared to here. So here it needs a positive charge. In the process of this YZ bond breaking, this Z now gains this pair of electrons, and now Z is now negatively charged with a lone pair. And it just so happens the lone pair and the Z can then form a new bond with that positively charged carbon. We call this a carbocation, and the result there would give us our product, which you've got there. So that would be an example of something called an electrophilic addition reaction. So we have an electrophilic addition because we're adding this electrophile. So we call this an electrophilic addition. Alkenes undergo electrophilic additions. Now, another type of addition reaction would occur with carbonyl compounds. And here we've got this compound here. And this compound here is either an aldehyde or a ketone, where this R group is either an alkyl group or a hydrogen. So the R group could be an alkyl group or a hydrogen. And this undergoes an addition. Again, addition, because we're going from double bonds to single bonds. Addition reactions go from double bonds to single bonds. Okay, there's a change in the bond order. Now, this thing here, this aldehyde or ketone, again, has got a polar bond. It's got a delta plus and a delta minus. So this electrophilic centre here will attract nucleophiles. It will attack species usually with a lone pair. So let's just say that I've got my nucleophile. I'm just going to call it Nu. And I'm just going to give this nucleophile a negative charge. This nucleophile could be neutral, and at which point the mechanism will be slightly different to the one I'm going to show you. But the first initial step is pretty much always the same, and it's the nucleophile forming a new nucleophile bond to the carbon. So the lone pair here is formed this new bond. That's nearly always the first step, regardless of what this species is. The next step is, again, always the same. It's the carbon-oxygen pi bond breaking. Okay, remember this is a pi bond and it's the weakest bond, so that's going to break first. That's going to give us an intermediate species. So what we've got there is we've got our NU now. And remember that this is now got a negative charge. So remember what's happened there. The pair of electrons in that CO bond, they've moved. And the pair of electrons that were in that bond are now as a lone pair. Again, the oxygen needs a negative charge because it had an equal share of 2. And now it owns the 2. So it's 1 electron up. Now, in nucleophilic acyl substitution reactions, what then occurs is that this carbon-oxygen double bond is reformed and it kicks something out, a Cl or a COOR. But in this case, what we've got is 2 R groups, or an R group and a hydrogen, or 2 hydrogens. And they are not good leaving groups. Okay, so if we consider, for example, the R group is a CH3, you'd be kicking out a CH3 minus ion. So let's consider, for example, this R is a CH3. You cannot kick out a CH3 minus ion, okay? Because this is not a weak acid. This would be an insanely strong acid, okay? Now let's just consider what we've done in previous examples. CH4 remember that this, we call this this conjugate base here. This there is like my acid. This here has to be a weak base, weakly base. It doesn't particularly want to gain this hydrogen. Conversely, this has to be an acid with a relatively low pKa. So, for example, carboxylic acid pKa is about 4 or 5. The pKa of this is going to be very, very, very high. It's probably around 40, which is way too high for this to be a good leaving group. So you're not going to be able to kick out a CH3 minus. So this is not going to undergo a substitution. You're not going to be able to kick out a CH3 or a H minus. Therefore, this will undergo an addition reaction instead. And what happens next is that the lone pair on that oxygen is being used to form a new OH bond, and you get this alcohol group being formed. Okay, so that will be my result. Okay, where in this case Y in effect is Nu. So these aldehydes or ketones, that's why they tend to undergo addition. They will not undergo substitution because the leaving groups here are not very good. In fact, they are not leaving groups at all, because the conjugate base form there it's not a weak base. In effect, the acid here is not acidic enough. Okay, so remember, for a good leaving group, okay, this conjugate base, the leaving group, has to be weakly basic, or the acid has to be a relatively strong acid. It's got to have quite a low pKa. Okay, so remember this nucleophile here, it could be charged. It could be like a H minus ion, at which point you get a reduction, a CN minus ion. It could also be an R minus ion, such as a Grignard, but it could be, for example, a nitrogen nucleophile, like an amine as well. But the mechanism there will be slightly different. So that is addition reactions. Remember, addition reactions occur when you've got species with double bonds, alkenes and aldehydes and ketones are species which undergo additions. This here would be called a nucleophilic addition reaction. So addition reactions there, electrophilic addition and nucleophilic addition. And remember, alkenes undergo electrophilic addition, aldehydes and ketones would undergo nucleophilic addition.